Okay, so in this second hour, I want to talk about the actual algebras that Tim and I used in our calculations. So in Prasad and Yeong's paper, they are able to deduce lots of things without getting their hands dirty with particular algebras. They know that they exist, have various properties, and that's all they need. Whereas for our calculations, we really need to realize these algebras. And so they've got to be, where's that gadget? So in brief, we've got a division algebra. There has to be a division algebra. There has to be an involution of the second kind so that the group G has all the properties we want. And we want to actually realize or concretely realize these division algebras. So the properties that we want are that when we look at the KV points of G, except for the one valuation in T0, this should be the simplest thing, SL3 KV, for every V that splits. For every V that doesn't split, we want the group to be isomorphic to this unitary group for a certain FV. We want GKV to be compact for a specific V0, T0 that we listed last time. And we want, for one Archimedean place, this group should be SU21. And in the case when the field isn't the rationals, we want the other GKV to be this compact thing. In the division algebra case, in the matrix algebra case, there isn't a T0, but in the division algebra case, the T0 is a specific valuation that Prasad and Yeong work out. So they know that there is such a thing. And what is rather more profound is that these properties determine the division algebra up to isomorphism or anti-isomorphism. So we have to talk about anti-isomorphism because with these algebras, there's a opposite construction. So when you have a division algebra, say, or more generally a central simple algebra, you can form the opposite algebra, whose elements are at one-to-one correspondence with the elements of D, but where the multiplication is screwed up. You see it's interchanged, it's reversed. So this is the Gopal, this is the paper that you quote, and I think I looked again. As you've left it off the list of references. I think. Yeah. Anyway, but anyway, you refer to it. So Gopal and Saiki know that there is such a D, and it's essentially unique up to this anti-automorphism. But what Tim and I need is to actually realize these division algebras. So here's where we start doing that. We start with a pair of fields K and L, and we choose a Galois extension of L of degree 3 with Galois group generated by, I like the letter phi, obviously, so phi is no longer the canonical map from SU21 to PU21. This is another phi. And we form this object here, D, which is a set of A plus B sigma plus C sigma squared, where A, B, and C are in M. And just formal sums, and we can make this into an algebra so that the cube of sigma is D, and that you have this non-commutativity. So perhaps, maybe lots of people aren't familiar with these objects. This is an example of simple algebra, but you all will have met the quaternions, and you can write the quaternions and where ij is usually called k, and so this is a set of alpha plus beta j, where alpha and beta are in C, and the rule is that for multiplication is that j squared is -1, and j times beta is beta bar times j. Okay, so it's obviously this construction here works in any where I've got 3 things here. I can have n things, and here's a well-known example with n is 2. Okay, so the C is a Galois extension of degree 2 of the reals. Its Galois group is generated by conjugation, and so you can think of the quaternions that way. And so this is what we call a cyclic simple algebra, but we have to prove that it's simple, first of all. So I'm going to go particularly slowly here because this is really important for our material, where we're going to use these things a lot. Okay. So when we form this object, there's always a homomorphism from the algebra to the matrix algebra over the bigger field that maps the sigma to this particular matrix. So if you work that out, the cube of that is D times the identity. And if you multiply, so it satisfies it satisfies this. When you apply psi, that holds. Okay, so if you have a general element of D, the image of it under psi is this thing, this matrix here. Okay, so this allows us to be working with matrices, not objects, sort of abstract objects in this division algebra. Okay, so they're matrices. But the downside is that we're working with matrices with elements in M, which is this field. So we're really interested in these fields K and L, which is, this is a quadratic extension. And then sort of artificially, we have this cubic extension of L in order to realize the division algebra. Well, to make the division algebra. Okay. So I talked last time about the reduced norm. So the reduced norm is, if you remember, if you have one of these algebras, you tensor it up with a bigger field, so it's isomorphic to, and then the reduced norm of an element is the determinant of the image of an element here. Okay, so here's an example of that. We've got the division algebra. We've got D embedded in M3 of M, and we take the determinant. And the answer is what's called the reduced norm, and that doesn't depend on the particular embedding we chose. So notice that this is an element of L. You see here I've got the norm of A. Here I've got D times the norm of B. Here I've got D squared times the norm of C. And this is a trace. This is a trace of A phi B phi squared C. Okay, so it's in L. Okay, and it's multiplicative because it's the determinant of psi of psi. Yeah, and So this is important because, amongst other reasons, to tell whether an element's invertible, you just have to know whether this reduced norm is non-zero or not. If it is non-zero, then there's the inverse. I'll leave the interested reader to check that for themselves. It's just, you just push the symbols around following the rules and out pops the identity. And of course, if the reduced norm is zero, then it can't be invertible because the norm of 1 is 1 and the norm is multiplicative. So, okay, so that's the reduced norm. And so this is an important proposition, which is again known from the 1930s in higher dimensions. Well, in this dimension, it's simple. With this particular dimension, D is either a matrix algebra or it's actually a division algebra. In other words, either it's matrix algebra or every non-zero element is invertible. And to tell which happens, you just have to work out when the element D, remember that's the element of L, which I use this is a straight D, not the curly D, which is the whole thing. So that's a curly D up there, and that's a straight D. So if D happens to be the norm of an element of M, then you're isomorphic to a matrix algebra. And if it's not, then you've got a division algebra. Okay? Now, this little fact is really important for us. We're going to use that in concrete calculations a lot. So I just want to go through the fairly short, well, indicate the very short proof of this. So if D happens to be a norm, you form this diagonal matrix here, C. And, oops. And you take a basis for M over L, and you form this matrix, capital theta. Its inverse has a nice form. It looks like this, where the zetas are a dual basis with respect to trace. So because the trace is non-trivial map, you can show that given a basis, you can find another basis where this happens. Okay? And then the inverse of this has this form. And you multiply the two together, the C from the previous slide and the theta, and you form J. And the claim is that J psi of psi, wait a minute, psi of psi, J of psi of psi, J inverse has elements, it has entries in L. So I think I'll leave that to the interested reader to check, but it's easy. If, for example, you take sigma, well, perhaps I should do it. I should do it. So psi of the particular element sigma has this D in the, okay, I believe. Let's go back a couple to check that. Yep, D in the, so that's psi of sigma. And if you then conjugate it by C to start with, and the inverse of C is easy to work out. The zeros. So multiplying by multiplying on the right by a diagonal matrix has the effect of multiplying the first column by this and the third column by this. Okay, so that gets rid of the right-hand multiplication. And then you're multiplying by a diagonal matrix on the left, and so you get 0 eta and 0 and then this is multiplied onto this, and so you get d over eta phi eta. But d is the norm of eta, so this is eta times phi squared eta, so I can replace this. Okay. And then, well, that's the hard part of the calculation. Let me leave the rest of it. It's too tedious. Okay, so that's the sorry. When I conjugate by J, I first conjugate by C, and then I conjugate by theta. So, well, it's pretty easy to see that when you conjugate something like this by something like this, you're going to get traces. Okay, so I'll leave you to check that. Anyway, so the upshot of all that is that these have entries in L, and so that means that the map that takes psi to this thing is actually has image in here. And it's clearly injective because if you saw, you see psi itself is obviously injective because just the ABC there, it's injective. And so we have an injective map from D to here. And then both objects have dimension 9. So it's an isomorphism. Okay. If on the other, to see the converse, if D is not a norm, then you can easily see that elements of the special form 1 plus b sigma, the reduced norm of that is this thing. See so this is an example of an element whose third component is 0. See, so if you'll excuse me, I'll go back up a couple of slides to this formula here, to the reduced norm. So if the C happens to be 0, see that term, and that term are all 0, that term is 0. And so you easily calculate that the reduced norm of a simple thing like this is this. And this can't be 0 because if it were, because D is not a norm. So therefore this can't be 0. And similarly, this can't be 0. And just a very small fiddle after that. Once you know that all of these, so therefore these elements are both invertible, and a small fiddle after that tells you that every element is invertible, apart from the identity. Okay, so that shows quite concretely that we have either a matrix algebra or a division algebra, and so either way we have a central simple algebra of dimension 9. But now we're interested in the case when the field L is a quadratic extension, totally complex extension of K. So L is, I'm going to write L as K with S adjoined, where S squared is minus kappa. Usually kappa, most of the time kappa is a positive integer. So, and we want to form an involution of the second kind on D. So we're going to assume not only that M is a normal extension of L, but it's a normal extension of the smaller field K. So then you can extend the conjugation automorphism of L to M. And if you think about it a moment, you see that the extended complex conjugate of phi of A is either phi of A bar or it's phi squared of A bar. So in the first case, the Galois group of M over K is abelian. In the second case, it's non-abelian. So there are two possibilities when you... Okay, so in the previous... So in the previous slide, we just had L, and M was a cubic extension. Now we're, and this is a Galois extension of L. Now we're supposing L is a quadratic extension of K, and so the question is whether and we're asking that M be a Galois extension of K, and it's just whether the Galois group's abelian or not. Okay, so here's a little lemma that if you're in the non-abelian case, and if your D that is remember the D is the value of sigma cubed, so it's an element of L. So if it's actually an element of K, then there's an involution of the second kind, which maps sigma to itself and maps the elements of M to the complex or the conjugate of it. So you see that iota of a general element of the algebra has to be this. So what's the proof of this? You just write this down and check that it works. So it's pretty easy to see that it's an involution. Anyway, it's got those properties to check for being an involution, and it's easy to do that. And when you do that, when you first apply iota and then apply the psi, you find that it's the conjugate of the adjoint of psi of psi for this particular f. Okay, so this is an example of an involution of the second kind on a division algebra. I think I've got an example now. Yep, so I'm taking the first of the field pairs, K comma L, where K is the rational field. So we have to cook up a field M, which is a Galois extension of L. In fact, a Galois extension of Q with non-abelian Galois group. So we choose this particular polynomial and take the splitting field. So it's a cubic polynomial. It's got a real solution. Thinking in terms of reals and complexes, it's got a real solution because it's cubic and cubic with real coefficients. And you can work out that the other solutions are this and its conjugate. So the splitting field is Q with I and Z adjoined. So it's L of Z of Z. So it's a cubic extension of L. The Galois group of M over L is phi, which is a map that sends Z to this thing. I didn't actually write what phi was there, but let phi be the map that sends Z to this, and is a field automorphism. And so you form this D, and you choose capital D to be 5. This is, why do you do that? Because you want this, to be a division algebra where this is the phi-vatic. Okay, and I'm going to skip the proof that anyway, this is a good choice. This is a good choice of D. It certainly is equal to its own bar. This is a nice Galois extension of the rationals with non-abelian Galois group. And by the previous slide, iota, there's an iota. The iota which sends sigma to sigma and A to its complex conjugate is an involution of the second kind. Yes?
I may just be repeating you, but if you didn't say it, the reason that's a good equation is because it's described as -1.
So you've got your hand in front of you now? Yeah. It's a...
The equation P of x, why that one instead of another one?
Yeah.
Well, many would do, but it's very important that the discriminant of that equation be -1. That's why the root of -1 occurs in the formula for the Galois conjugates.
Right, okay, okay. Yep. Yeah, Tim, by the way, found all these, years ago, these particular cues, but so what his reasoning was for filling it was things like that, but I guess I took his results and tried to justify it after the fact. Okay, so that's an example of a involution of the second kind on a division algebra. Now, I'm saying a few things more about this case. Remember we have this behavior of the involution under psi. Another way of putting that is that okay, so these psi's, the image of an element is unitary with respect to that particular f. Okay? Now, I want to change that so that it's unitary with respect to f0, where f0, remember, is the matrix used to define SPU21. Okay? Well, if you do a little calculation, you find that with this particular delta, f is equal to this. And so here's a calculation which is simple, but I'll leave it to the reader. That when you take, because of this property here, when you conjugate by delta, the result is unitary with respect to f0. That's because f equals this. Okay. So that means that when you conjugate by delta, you're mapping this group here into SU21. It's because here, if you have an element satisfying this, that means it satisfies this, and so its conjugate is unitary with respect to f0. In other words, it's in U21. And if you ask that the reduced norm is 1, then you're in SU21. Okay, so this is an example of one of the properties that you want your algebraic group to satisfy. When you've only got one Archimedean place in this instance, because the field is just the rationals, you want that this should be SU21. And this is more or less the proof of that. Okay, now, in most of the cases we played with, we chose an M so that the Galois group is abelian. And now we choose a D, which satisfies D bar D as 1. When you do that, there's an involution of the second kind on the division algebra. On the algebra, I haven't proved yet that it's a division algebra, but on the algebra, there's an involution of the second kind, which maps sigma to its inverse, and does the same thing as before on the elements of M. So again, you can just write down what it has to be. You can write down this formula and check that it's an involution of the second kind. Okay. This time, when you do the calculation, this is a little bit different from what we saw before, and we're using the fact that phi of the bar of something is the bar of the phi of something. It's an abelian Galois group that makes it work. So this time, when you apply psi to the iota 0 of psi, you just get the conjugate transpose. Okay. Now, we actually use a slightly more complicated involution of the second kind. We conjugate it by an element T. And provided we conjugate by an element which is real, so to speak, we do get an involution of the second kind. You need this property, otherwise you screw up the fact that iota of iota is the identity. And then when you do the calculation, you find that psi of iota of psi is this, for a slightly more interesting looking t, f. Okay? It's sort of obvious because, yeah, well, this here is psi of the element t. So anyway, it's a little calculation. So I'll do an example. So here's an example where the field K isn't the rational field, it's Q with the square root of 5 adjoined. And we take L to be, we adjoin the square root of -3. Okay, so here's K, here's L. And we choose this M. It's K with the primitive root of, 9th root of the identity adjoined. Okay. So when you do that, you see the cube of this psi, of this zeta rather, the cube of this zeta is a primitive cube root of 1. So I think that's right. So if you're doing elementary, like first year university, and you're playing with complex, solving the quadratic there, this is the answer. And so that zeta cubed is an omega satisfying this, and so. So omega. So twice omega plus 1 is the square root of -3. Okay, so that explains why mapping the square root of 3 to this embeds L and M. Okay, so we've got a sort of slight modification of a cyclotomic field here. The Galois group is cyclic generated by this thing. So we've got an isobelian Galois group here, and the Galois group of M over just L is you just take the square of this. Okay, so this automorphism of M fixes the elements of L. Okay. So you form D as before, and this time you choose capital D to be 1 plus RS all over 4. So this RS, you see, R is the square root of 5 and S is the square root of -3. So this is a square root of -15. Okay. Okay, so d bar D is 1. Okay, so you do get an involution of the second kind, mapping sigma to sigma inverse and A to A bar for this particular one. Okay, now, as I say, we modify this to, by conjugating by an element T, which is real. So T bar is T. And this is a T we choose here, where W is zeta plus zeta inverse. So this is, remember, zeta is a primitive 9th root of unity, so you can assume it's the e to the 2 pi over 9, And so this is twice the cosine of 2 pi over 9. And I've just written down a couple of facts about this W. It satisfies this cubic. It's when you apply the phi of the previous slide to it, you get this. And when you apply the second one, you get this. So the reason you do this is the following. When you embed your field M into the complexes, mapping R to the positive square root of 5 and W to twice the cosine. Okay, this is why you do that is clear from here. What you find is the image of t is positive, the image of phi of t is positive, and the image of phi squared of t is negative. If, on the other hand, you embed M into C, mapping R to negative square root of 5 and W to the same thing, we find that the images are all positive. So remembering that our form F that comes out of iota is this. You see, when you use the first embedding, which maps R to plus square root of 5, you see that I'm being a bit sloppy here. This T means the image in the complexes of T under that embedding. You see, this is T is positive, phi of T is positive, and phi squared of T is negative. And so when you take the absolute values, well, first of all, the star is just itself. And everything is diagonal, you see, and this is this one has absolute t to the 1/2 each time. So when you get this, you get this, and then have I got this right? So this is, oh no, with the F0 there, this one has a minus sign in front of it, right? Because F0 is 1, 1, minus 1. So I'm multiplying diagonal matrices together, so everything is easy. And so you get this, but then t is positive, so you get t. This is phi of t is positive, so you get this. And phi squared of t is negative, so its negative absolute value is itself. Okay. If, however, use the other embedding, and so this means the image under the other embedding of F, and this is the image of delta under the other embedding, you find that F is just, so the absolute value, well, you don't have an F0, you put the identity there, and you don't have a minus sign there, and you again have this. So that F is this, and so when you conjugate, that you see that you're going from a psi, which is unitary with respect to F, to a conjugated thing, which is unitary with respect to the identity. In other words, something in SU3. So by making that choice of T that we made on the previous slide there, that peculiar choice of T, we get that G of KV is isomorphic to SU2, one for one place, one Archimedean place, and it's isomorphic to SU3 for the other. Yes?
So possibly someone would want to know, how did we find that particular T? And the answer is the stupid answer. We used small coefficients and a little computer program that calculated all of these values of T and A of T as explained, and we found one that had where they had the right signs, so everything was as small as possible.
Yeah.
No intelligence involved.
Yeah. Well, the intelligence is knowing what to look for. Yeah. Okay. All right. Now, let me in this case show that we do have a division algebra. Okay, so if you remember, this is, so the T0 in this case is for the two-adic valuation. So, so if you do a little calculation, you find that 2 is inert so the prime 2 remains prime in this field, and so there's just one two-adic valuation. And I want to show, so in the Prasad-Jung paper, their division algebra has to be such that this is the one place where the tensor product remains a division algebra. And so I want to show that the thing is not a, to show it's not a division algebra, I use the criterion given right at the beginning, where you have a division algebra precisely when the capital D is not a norm. Okay, so I want to show that the particular D I chose, which remember was 1 plus RS over 4, so this is, so I want to show that that's not a norm, okay? And to do that, you, one way to do it is as follows. You play with the two-adic, use the two-adic valuation on K. So if you do a little calculation, you see that 2 is rho times rho bar, where rho is this particular element of an algebraic integer on L. And if you do another little calculation, you find that the D is rho over rho bar. Okay, they're just really baby L calculations. And so that means that for the valuation on L corresponding to that prime ideal, so remembering that the valuations correspond to prime ideals, here's a valuation, the one corresponding to that prime ideal, because there's a row to the 1 here, that means W of D is +1, and because there's a rho bar on the bottom, that means that the valuation corresponding to this ideal, evaluated at D, is -1. Okay? But all the other valuations on L give answer 0 when you apply them to D, because D only involves because D only involves rho and rho bar like this, all the other, if you evaluate either rho or rho bar at another valuation, you get 0. Okay, it's only for the two-adic valuations you get a non-zero answer. Okay, so this, when you go up to M, you find that these valuations are inert. So this remains prime. I mean, you can do it various ways, but the easy answer for me is I just ask Magma, there's a command in Magma, is prime? And it comes out true or false, see? And it's not really a proof, but it's certainly quick. Anyway, so Magma verifies this is prime. What that means is that, the valuation here has a unique extension to M. Let me call it W tilde. And furthermore, that it takes integer values. Okay, there's no ramification involved here. Okay, so because there's a unique extension, it's got to satisfy this for any element. So supposing that D were a norm, then you see 1, which is the valuation of D, would be, because W tilde is an extension of W, that would be 1. But then valuations of products are sums, and so the valuation of this product is the sum of the three valuations, which are all equal, and so you get 3 times W tilde of eta, and this takes integer values, so we have a problem. Okay, so D is not a norm of an element of M, and so we definitely have a division algebra. Okay. All right, how we go for time? I've got 10, 15 minutes, yeah? Approximately, yeah? 15, did you say? 15? 15, yeah. Okay, so I'm going deaf in my old age, sorry. So I gave 2 examples of division of these algebras. One for 2 field pairs K, L, and believe me, you can do the same thing for the other 7. You can cook up a field and make a division algebra. You can make an algebra for each of the other 7. The proof that you actually have a division algebra is very similar to the one I gave for C2. There's one tricky case, C18. It turns out that V0 is a 3-adic valuation, and it turns out that this value, the 2 extension of V0 ramify an M. Okay, so that means that my little argument where 3 times something equals 1 gave a contradiction doesn't work, because the W tilde of eta, it could be a third, you see. So one has to be more careful in that case, and I'm not going to go into the care that one takes, but it's true. So all of these are division algebras. So now I want to very briefly talk about why these have the other properties that we wanted the algebraic group to have right at the beginning. So we want to find these GKVs for the various places. So if you stare at the Prasad-Young paper, you see that at a certain point they tell you that the K, if you have a field containing K, the definition of G of K is this thing. So you form a tensor product over K of D. Now, this requires a little bit of thought. So first of all, we've got this involution of the second kind on D. So that's a K-linear map. And so it extends uniquely to a K-linear map on this tensor product, which is still an anti-automorphism. What about this reduced norm sub K? Gopal didn't talk about this at all in his paper, but maybe this is one way of dealing with that. You've got the psi here that maps D to here. Now you can take the tensor product and you get a map into the matrix algebra where the entries are in this tensor algebra here. And you can take the determinant of something in here and you get an element initially which is in here, but in fact is in here. Anyway, so this is what you have to do to set up the meaning of this line here. So the involution of the second kind extends to a map on here, and the reduced norm, originally just defined on D, extends to this thing. And you form G of K. And there's also the adjoint. In the interest of speed, I might just skip that for the moment, but that is important for us. But how this group behaves for the various capital Ks depends on whether the valuation splits or not. So I'm going to be only looking at the case where capital K is K sub V, and it depends on whether V splits or not. And I mean, a funny thing happens. In one case, you get just a linear group, and the other case, you get a unitary group. And so I think deep down, the simple reason this happens is that when you have a field containing K, which happens to contain L as well, then this tensor product is a direct sum of two fields. But when L doesn't embed in K, the tensor product is a field. This is elementary. Here are the isomorphisms. So this dichotomy of behavior goes over to the group algebra, to the group case. So when V splits, then you see all the unitary aspect is gone. So you just have SL, PGL, and so on. Well, the second thing that can happen, though, is that these are compact. This is compact. That happens when you have a division algebra. So I want to convince you that with the Ds that I have constructed above, we do get this behavior. We do get this behavior. In all the other talks I've given at this point, I've just said this is well known and slid right over it. But Gopal or someone, maybe you can tell me a reference where I can do this very quickly. But the way I see how this works is that you look at, in the case when V splits in L, you can embed L in K, and you get a map from the tensor product you're interested in to a direct sum of, you get to a direct sum of, or product, if you like, of two simple algebras, an algebra and its opposite. So this is induced by this K-linear map. Okay, so if you think about it a little bit, you see that this gives you an isomorphism from this algebra over KV to this direct sum of two simple algebras. Then you've got the iota map, and down here you've got the this very simple involution of the second kind, or involution, just involution. You take a pair x comma y op to y comma x op, and you find that this is a commutative diagram. You also find that the norms behave the way, in this way. You've got this map that I mentioned before. You've got the reduced norm map, sub KV, and here you've got the map that takes the pair x comma y up to this pair, and this diagram commutes. So the upshot of all that is that when you take an element from here, psi in here, and you look at its image under H over here, then it says this unitary property over here, if and only if the image has the corresponding property over here. And so that means this times y comma x op is the identity, and so that comes down to simply this. And similarly, this norm thing holds if and only if the two norms are equal. So because of, well, that's clear from this commutative diagram. Okay, so you conclude that this, remember, is the set of elements of the K tensor product which have reduced norm 1 and satisfy the iota property. You get these two isomorphisms. So this sort of factorizes the problem. We're trying to understand what happens to these groups here. So the first step is showing that they're isomorphic to these things like this, which involve a simple algebra so we're dealing with division algebra over L. And so when you take the tensor product, it's, that's again a simple algebra over KV now. And now you have to work out what these things are. Well, there are two cases. It's complicated, it goes on and on and on. But it depends on whether, M embeds in KV or not. So L embeds, we're dealing with the split case here. So when L embeds in KV, so whether M embeds or not. If it does embed, then the isomorphisms are just sort of obvious things. You have this map and they induce natural isomorphisms. But when M doesn't embed, you have to do a bit more work. In that case, your field M is going to look like this. When you take the tensor product with L of KV, you get another field. And this tensor product is a cyclic algebra of the sort we looked at before. So when the D happens to be a norm, you get a matrix algebra, and the isomorphism you get involves that conjugation by J for these things that we looked at before. To see why D is a norm, we use a big theorem from, let me just skip that. We use a big, I'm not sure how big it is. In local class field theory, this is probably a small theorem, but it's a non-trivial theorem, that if you have a local field and a cyclic extension of, so you have a local field K, non-Archimedean, and a cyclic extension of K of degree L, then the image of the norm map has index n in the codomain. And in the case when L is actually an unramified extension, the image is precisely, I didn't mean this, I meant divisible, congruent to 0 mod n. That's right, yeah. I don't want equal 0, I want equal 0 mod n. Okay. So in particular, you see these Ds that we have, they have valuation, non-zero valuation only at the two so this D we have in that particular example, you see that if you have a valuation that is an extension of the two-adic valuation, you get and you can't apply this theorem, but if a WD is 0 otherwise, see, so when you take when you take a W which is not an extension of the two-adic one, you see this has valuation 0, and the theorem guarantees that it is a norm. And therefore, all this, the last 3 or 4 slides work. Let's see, what yeah. Yeah, so you do get these isomorphisms because the D is a norm by the theorem I went through in detail right at the beginning. Okay, so you do get this behavior. If, however, if you deal with the V, which is an extension of the two-adic, you get a division algebra still. The D is not a norm, and the fact that this is compact is, well, this is a well-known and easy, so here's a proof which I can't give, but if you have a local field here and this is a division algebra, this object on the right is compact. You can easily see. So there's the proof. The slides will be available so you can look at your heart's content. Anyway, so what I haven't talked about is what happens when the V doesn't split. Then you get some different commutative diagrams. You get a different. The important thing is that when it doesn't split, you get this isomorphism, and this algebra admits an involution of the second kind. And well, I think I'd better stop. I've run out of time. So.
Are there some questions? Comments?
Okay, again, this is simple. You might ask, with the many possibilities for M available, why did we choose one instead of another? We just looked for the simplest possible M. One way of defining simplest possible, we want an M in which few primes ramify, because as in the case he was talking about a second ago, when the prime does ramify, you have to worry about doing the calculations in a special way. If you can arrange it so that only a few primes ramify, your life is easier. But again, there was no reason we had to choose one M instead of another, and we didn't do it according to any fully systematic system. We just chose something that seemed simple, where a few primes ramified.
Thank you.
That's the sort of question I like.
Other questions? Well, thank you again.
Okay.